Hello, this is Bryson, and in this video I would like to talk about the dot product theorem. Well, in order to talk about the dot product theorem, we should probably start with talking about what a dot product is. So the dot product is basically a way of multiplying two vectors. So let's say we have vector A and vector B. Okay, and then let's say vector A has components AX and AY, and vector B has components BX and BY. So the way that we represent a dot product is with a dot. Yes, very creative. So A dot B and let's AX, a vector of AX and AY dot a vector of BX and BY. So what does this equal? Well, the dot product is defined as AX times BX plus AY times BY. So that's what a dot product is. And the dot product theorem just simply states that this also equals the magnitude of vector A times the magnitude of vector B times the cosine of the angle between them. Let's call that theta. So that is the dot product theorem. Okay, so how do we prove this? Well, one way to prove it is to redefine the axes. So let's say we have vector A here and vector B here. Well, on this axis. We could draw different axes with one of the axes lying on vector B. So what does this make? And the reason we could do this is because the dot product is basically a relationship between two vectors. And no matter what our definition for the axes are, the relationship between these two vectors shouldn't really change. So once we redefine the axes, what are the components? Well, for vector A, you have this would be AX. So from this would be AX right here. And then let's make this AY. And then let's make BX is itself. This is BX. And then there is no BY. And then let's call this angle, which is the angle between them, theta. Okay? So then let's just follow what we have here. So the dot product is equal to AX times BX times plus AY times BY. So AX is simply the magnitude of vector A times cosine theta, and BX is just the magnitude of vector B, because vector B now lies on the axis. And then we need to add AY and BY. So what is AY? Well, AY is the magnitude of vector A times sine theta. And then what's BY? BY is just 0. So you're multiplying by 0, so that just equals magnitude of vector A times the magnitude of vector B times cosine theta. Now, that is essentially my proof for the dot product theorem. I know there's another proof that has to do with the law of cosines, but this is, I feel like, much easier to understand. Whether or not is an official proof, I'm not entirely sure. And if you have the answer to that, please tell me in the comments below. Well, I have something else to show you. So, some of you guys may think that since I redefined the axis, it might not work if I didn't redefine the axes. So let's start over again. Okay. So this time I won't redefine the axes, and then I'll start by defining other things. So we still have vector A here and vector B here, right? Nothing changed there. Oh, I'm gonna call this angle theta, and I'm gonna call this angle alpha. So that's still understandable. And then I'm gonna call this is AX. Oh, this is AX. And AY is here. And then let's just say BX is here. And then BY is here. So I'll bring this closer. So yeah, so this is AX, which is the component of the X component of A, and this is AY, which is the Y component of A, and then this is BX, which is the X component of B, and then this is BY, which is the Y component of B. So what is AX? Okay, so AX would equal cosine of theta plus alpha times the magnitude of A. Right? And then AY now equals the sine of theta plus alpha times the magnitude of vector A. What about BX? BX is just equal to cosine of alpha times the magnitude vector B. And then BY is equal to sine alpha times the magnitude of vector B. So we essentially just do the same thing. So AX times BX. Well, we could first we could expand this addition of angle, cosine of the two angles, of the sum of two angles, when we multiply AX times BX. So AX times BX would equal cosine of theta times the cosine of alpha minus the sine theta sine of alpha. So this is basically that. And then you multiply this by cosine theta and the magnitude of vector A and the magnitude of vector B. So we could distribute this cosine theta into, cosine alpha. So you got cosine theta times cosine squared alpha minus sine theta sine alpha cosine alpha, and this is all multiplied by the magnitude of vector A times the magnitude of vector B. Right? That's all good. Nothing too complicated there. You just probably need to know that how to expand this. And then we do the same thing for AY times BY. So AY times BY is equal to, you expand sine theta too. So you get sine theta cosine alpha plus sine alpha cosine theta, and this is multiplied by sine alpha and magnitude of vector A and the magnitude of vector B. See, and then we'll multiply the sine theta into. So you get sine theta sine alpha cosine alpha plus sine squared alpha cosine theta, and this is multiplied by magnitude of vector A as a magnitude of vector B, right? So if you remember, the dot product is ax bx plus ay by. So all we have to do now is just to add these two things. But as you can see, we have the magnitude of vector A and the magnitude of vector B multiplied in both of these things. So we could distribute that out. So ax bx plus ay by is equal to magnitude of vector A times magnitude of vector B times cosine theta cosine squared alpha minus sine theta sine alpha cosine alpha, and plus, since there's no more room here, I'm just gonna write it here. So plus sine theta sine alpha cosine alpha, and then plus sine squared alpha cosine theta. There we go. And then if you notice anything about this, we see that these two terms cancel out. So we could just cancel them. And we also see that there's a cosine term both here and cosine theta term both here and here. So let's distribute that out. So we get that this equals to magnitude of vector A as a magnitude of vector B times cosine theta times cosine squared alpha plus sine squared alpha. And as you guys should all remember that sine squared x plus cosine squared x equals 1. So this just becomes magnitude of A times the magnitude of vector B times cosine theta. which is exactly the same thing that we got before, but we just didn't redefine our axes this time. Okay, so this should essentially work in 3 dimensions, or at like any dimensions, because between 2 lines, you should always be able to draw a plane through it. But, so like, no matter how my 2 vectors are situated, you could always there's always a plane between them. So yeah, that is essentially the dot product theorem. So I'll show you each of the papers again. So this is a dot product theorem, basically. And this is the way to do it with redefining axes. And this is the way to do it, the way to prove it, I guess, without redefining your axes. So yeah, there you go. Well, now it's time to say goodbye, and I guess if you liked the video, you could leave a like, and if you didn't like the video, I guess you could leave a dislike. I don't really care, so goodbye.